What up, bros? Okay, so today we're going to talk about parametric equations. So, with parametric equations, you'll always be given a set of two equations, that define some kind of a curve or conic section, so parabola, ellipse, etc. And basically the idea behind a parametric equation is that they include the regular terms of x and y, which are just horizontal and vertical axes. But then they also include t, which is the parameter for the equation. And that just basically means that, a parameter is sort of a limit. It's something that is, defining the curve. So the parameter, you could think of it as anything, that kind of defines how the curve will happen. So I like to think of it as time since it's t, but it's not always going to be time. But just if you think of something that happens over time, like if you throw a ball and you're plotting its position, then basically the parameter for t is the time. So if it starts right here and then as you throw it, it goes down and you're calling this the ground, then your parametric equation is just that you're defining that term, the ball's position, over a certain amount of time. That's time is your parameter. So then like at t equals 1 second, it's going to be right here. And at t equals 3 seconds, it'll be right here. T equals 5 seconds, let's say it's almost the ground. So that's just basically what it is. So now that we've defined what a parameter is in a parametric equation, there's basically two ways that you could figure out really how to graph this. So you're given two equations. Let's say x equals t squared minus 1 and y equals 2t. So let's say you're given those two equations. So you could either first just start plugging in values for t arbitrarily. And then you could take those, plot them, whatever you end up getting. Actually, it doesn't look like that. It's the other way, but I can't flip. Okay. Well, it's like this. But it doesn't matter. You plug in values for t, get an output x and y value, and then you see what the graph looks like, and then after that you can find the rectangular version of the equation, which I'll show you in a sec. Or you could find the rectangular version first and then plug in values into that. So plug in values for x and y, like normal. So the better way to do it is this first way, which is why Glennon taught us to do it that way, because you can plug in values for t, get your curve, and then once you find the rectangular version of the equation, you can make sure that your given graph of points matches the rectangular version you find. So it's kind of an automatic built-in check for yourself. Okay, so I'm just going to go through 3 or 4 from, actually I'm just going to take them straight from section 9.5, which is the parametric equation section, for those of you playing along at home. Yeah, and actually I don't know why I just did that. I hate myself. So I'll start with number 9. This one's gonna turn out to be a parabola. So they give you x equals t plus 2, y equals t squared minus 2. Oh wait, no, y equals t squared. And then they sometimes will give you a limit too, so -2 less than or equal to t and less than or equal to 2. So all this is telling you is which area of the parabola to graph. So only the values along where t is equal to -2, -1, 0, 1, or 2. That's just telling you like what section. So what you do, just start by making your little graph, chart, of x, y, and t values. So if you plug in t0, 0, 1, 2, -1, and -2 because those are all along the parameter. When t is 0, x is 2, and y is 0. When t is 1, x is 3, and y is 1. When t is 2, x is 4, and y is 4. When t is -1, x is 1, and y is 1. And when t is -2, x is 0, and y is 4. So then you can, let me just get a graph up here because if I drew it, it would be a mess. So yeah, got that. And then what you can do is just plot it out real quick. I don't know how to make that bigger. So you have the point 2, 0, 3, 1, 4, 4. Obviously label these points when you're doing them. 1, 1, and 0, 4. So that's a parabola that comes in right about there. Now, if you didn't have, that sucks. If you didn't have this thing right here, then you would go ahead and graph the entire parabola. But since they give you that limit on the t values, you only want to graph this section of it because that's where -2 is less than or equal to t is less than or equal to 2. Now, the way you'd find the equation for that, they call it eliminating the parameter. So all you do is simply solve both equations for t. So in this case, t equals x minus 2. In this case, t equals root y. And then you'd set those equal to each other. So root y equals x minus 2. Square both sides, you get y equals x squared minus 4x plus 4. So that's your parabola. Y equals x minus 2 squared plus 4 minus 4. Y equals x minus 2 squared. So then your vertex there is at 2, 0. Your axis of symmetry is at x equals 2. So that's the quick, easy check to find the equation after you graph it. Okay, so the next one I'll do is 15. That one looks like bundles of fun. So sometimes they'll include sine and cosine functions. Don't get worried about it. It's basically just the same exact idea. So x equals cosine t, y equals sine t. This is a circle. So, and then they give you 0 is less than or equal to 2 is less than or equal, or less than 2 pi. So basically that's just telling you that it's all the values along the unit circle. Because, so you could think of t as sort of the angle that you're going to swing out for those points. So same deal. Make your x, y, t chart. Plug in some values in radians since your parameter is in radians, so you want to plug in some of those. So let's just do the standard values: pi over 6, pi over 4, pi over 3. Let's do pi over 2 for good measure, and then, well, I can't really fit anything, but we could do others. So, when plugging in pi over 6, cosine of pi over 6 is root 3 over 2. Sine is 1 over 2. Cosine of pi over 2 is root 2 over 2. And sine is root 2 over 2. Pi over 3, cosine is 1/2. And the sine is root 3 over 2. And for pi over 2, cosine of pi over 2 is 0, and the sine is 1. So you just plot those points right quick. Root 3 over 2 is approximately 0.866, and root 2 over 2 is approximately 0.707. So, I mean, you can basically figure out where they go. Let's call this 1 right here, just so I have a little more increments. So you got 0, 1 at pi over 2. At pi over 3, you have 1/2 root 3 over 2, somewhere there. That's not accurate, but something like that. Pi over 4, you got root 2 over 2, root 2 over 2. And pi over 6, you got root 3 over 2, 1/2. So basically, this graph is just the unit circle, and you draw it in like that. Because the values go up all the way to 2 pi. So that's one full rotation around the unit circle going this way. And then you would say this value is t equals 0 radians, t equals pi over 6, t equals pi over 4, etc. Yes. Okay. And then just to find the regular sort of equation for that, you kind of have to go through some fancy footwork, since you can't exactly eliminate the parameter of t without, taking inverse sines and cosines, and that doesn't really help you anyway. So, when you normally, this would be like the equivalent of solving a system of equations by elimination instead of substitution. So, if you just look at these two equations, you know that cosine squared of x plus sine squared of x equals 1. So if you square both equations and then add them, so x squared plus y squared would equal cosine squared of t plus sine squared of t, then you would get x squared plus y squared equals 1. And that is the rectangular equation for this circle. It's a circle with a radius of 1 and centered at 0, 0. So that's your check, you're right. So next we'll try the graph of an ellipse, which is, going to be something like 31. You'll get to kind of spot them just by the forms of their equations, because you can tell when it's going to turn out to be equal and when it's not. When it's a circle, parabola, ellipse, hyperbola even. So they give you x equals 2 cosine t and y equals 3 sine t, where the parameter is limited to, where'd that go? 0 is less than or equal to t is less than 2 pi. So that'll be a common one for values where you're plugging in values for radians. So if you get this by now, obviously turn the video off, stop listening to me, but I'll just take you through a couple more. So then, make your chart x, y, t. T is 0 radians, pi over 6, pi over 4, pi over 3, pi over 2, if we can fit that in. So at 0 radians, the cosine is 1, so that's a 2, and the sine is 0, so that's a 0. Cosine at pi over 6 is root 3 over 2, so that's root 3. And the sine is 1/2, so that's 3/2. Pi over 4, root 2 over 2 times 2 is root 2. 3 times root 2 over 2 is 3 times root 2 over 2. Wow, revolutionary. I don't know why that's up there. For pi over, that's like this. For pi over 3, cosine is 1/2, so that's a 1. And the sine is root 3 over 2, so that's a 3 root 3 over 2. And for pi over 2, the cosine is 0 and sine is 1, so that's a 3. So, with graphs like this that aren't as straightforward, like an ellipse like this, you can do it like this, obviously, but you're going to get kind of weird values when you're plugging them in because of the nature of the points on the unit circle. So this shows you kind of just where the other way comes in handy, where you convert it to rectangular first and then do it. So the book tells you for these problems, for this section, to convert to rectangular first and then graph. So when you see that it's not going to turn out nicely when you're not converting to rectangular, then that's when you should convert to rectangular form first and then start plugging in values of x and y to get your normal stuff. So these, when you approximate them, the values turn out to be somewhat like this. So those are your angles, and then you can see the ellipse kind of come in there like that. That's just a rough sketch, but as you can see, when you find the actual rectangular form of the equation by, this is once again some fancy footwork, but so using that same idea that cosine squared t plus sine squared t equals 1, you want to solve for cosine t and sine t, so the equations would then become x over 2 equals cosine t and y over 3 equals sine t, and then you want to square both and add them. So you'd get x over 2 squared plus y over 3 squared equals cosine squared t plus sine squared t. And then you get your regular form of an ellipse, so x squared over 4 plus y squared over 9 equals 1, like you're used to, and then you can graph from that. And as you can see, that'd probably be a lot easier to convert first and then switch. So just remember that idea of squaring both to get the 1 on that one side. Alright, and the last one I'll take you through is probably the toughest one yet. 35, which is x equals secant t, y equals tangent t. So this is going to be a hyperbola, as you'll see, but you might not be able to spot that one right away, but you probably will if you remember that if there's an inverse sine or cosine or tangent in there anywhere, then it's probably going to be something weird like a hyperbola. So, like I said in the last one, you'd probably want to convert this to rectangular first, but just to, keep with what I've been doing, I'm going to do it the other way. But if you do it the first way, you'll probably have an easier time. And you'll see that in a second, but I like to do it this way so you have a check. So plug in 0 radians, pi over 6, pi over 4, pi over 3, and pi over 2. Just remember secant of t will be the 1 over cosine of t. So that's just the reciprocal of the cosine. So, secant of t. Yeah, so the points will get interesting here, as you'll see. So, just going to fill this out real quick. For 0 radian secant is 1, tangent is 0, 4 pi over 6, secant's 2 root 3 over 3, and tangent's root 3 over 3, pi over 4, root 2 and 1, pi over 3, 2 and root 3, and 4. Oh, well, I'm doing it again. But, yeah. And then for pi over 2, since the cosine there is 0, 1 over 0 is undefined, so you have no point there, really. And the tangent, therefore, is also undefined, since cosine is in the denominator for both. So you have an undefined point at pi over 2, which means that at pi over 2, or along the y-axis, there are no points. So that kind of is a good indicator that this is, in fact, a hyperbola. So you plot these points, you get 1, 0, 2 root 3 over 3, root 3 over 3, something like that. And they go out like that, so on. So you're going to end up with a hyperbola here and here. And the way you can kind of prove that is maybe don't draw in the graph. If you're going to do it the way I'm doing it, which I suggest against because I'm just doing it, as a check, I would say plot in those 5 points and don't draw in the graph yet until you get the rectangular equation to confirm, and then you can figure out where the rest of the graph goes so that you don't have to plug in millions and millions of points to get the entire thing. So, to solve for the graph here, just change it into x equals 1 over cosine of t and y equals sine of t over cosine of t. So then x cosine t equals 1. Y cosine t equals sine t. And in this case, you could solve for cosine t both times. Cosine t equals 1 over x. Cosine t equals sine t over y. Oh, no, I lied. I'm joking. You don't actually want to do any of that. Ignore that. Ignore me. I'm wrong. Easy way to do it is square both and then subtract, because you know the identity secant squared of t minus tangent squared of t equals 1. That's one of your identities that you have memorized, just like me. I have them all memorized. So you square both equations up here and then subtract them. So and you end up getting x squared minus y squared equals secant squared of t minus tangent squared of t. So then you get x squared minus y squared equals 1. And that's your standard form of that hyperbola with that vertices, as you can see, at 1 comma 0 and negative 1 comma 0. Your axis, your conjugate axis at y equals 0, transverse at x equals 0. And that's just your standard hyperbola. And you can confirm that your points are on it, and then you can just graph out the rest from the equation.